Hello, my name is Gianni Goretti. I am a postdoc researcher at TU Dublin in Ireland, and I will be presenting a piece of work on data cleaning for power curve modeling and wind power forecast evaluation. First of all, I would like to thank my supervisor, Professor Aidan Duffy from TU Dublin, and the modeling team from ESB who provided the data presented in this research. The objective of this work is mainly to develop a Python module for wind turbine data cleaning. So cleaning data at the wind turbine level with the objective of having clean data for power curve modeling or wind power forecast evaluation. The code that is presented here is available at the Github repository at the address that you see. There are a few assumptions on the quality of data and the format of data that are required for implementing this Python module, this Python function. It is assumed that the data are consistent, so they're all presented in the same format. Let's say we have inputs from different SCADA systems. They have to be all in the same format, and the data are uniform, so all the measures are in the same, expressed in the same unit. So for example, wind speed in meters per second, timestamps have the same UTC offset, power is expressed all as normalized values. The variables necessary are wind speed and power, as I was saying, normalized by the rated capacity of the turbine for each of the turbines. And the format of the data is the classic data frame, if you like, a spreadsheet, with first column being the index and then one column per variable. So one set of columns for the wind speeds and one set of column for the power outputs. As I was saying, the data is pandas data frame, and the columns are called with the names that you see. So wind speed underscore and then WT and the number of the turbine, and same with the power. There's only 3 packages required for the implementation of these function, and there are pandas, numpy, and matplotlib for visualization purposes. Coming then to the methodology and how the function is set up and how it works. The function is called clean turbine, clean underscore turbine, and it takes a few parameters that you see here. So the first one being obviously the data set, the data raw, then the number of turbines, WTN, the characteristic wind speeds of the turbine, so cut-in wind speed, rated wind speed, and cut-out wind speed, all expressed in meters per second. Then the multipliers k underscore up and k underscore low that will be used to detect, to define what is the threshold to detect outliers at the upper and lower end. And then the parameter anomalous, which basically determines whether we are keeping or not the anomalous periods in the data set, and maybe this will be a bit clearer further ahead in the presentation. So firstly, the function checks for missing data, checks for the completeness of the data set, and prints out how many wind speed values are missing and how many power values are missing. Then checks for extreme values at the univariate level, so checking wind speed per se and power per se, so checking for negative values and very large values of these two variables. and then checks for extreme values in the bivariate distribution. So it does so by looking at the power curve of, so basically looking at wind speeds against power values and doing some statistical analysis to detect the outliers. After screening the data, there are three possible diagnoses. So data can be normal, erroneous, or anomalous, and if they are anomalous, they are flagged. Looking at a power curve for a wind turbine, where you can see the cutting wind speed, the rated wind speed, and the cutout wind speed. Um, the erroneous data regions are in red, colored in red here, and to the left of the power curve, and to the far right, if you like, of the power curve. And the anomalous data region is the one under the power curve when wind speed is still less than the cutout wind speed. And depending on the diagnosis, then the treatment is data are kept if they are normal, they are removed if they are erroneous, and if they are anomalous, as I was saying, they get flagged and they can either be kept or removed depending on the researcher's decision and depending on what the aim of the cleaning is. This is done through the anomalous parameter in the function. So if the parameter is set as false, as it is the default, all the anomalous data are removed. Whereas if it's set to true, the anomalous data are kept. Some examples of when one would set the parameter to false or true. Let's say we want to use the turbine data, clean them to develop a power curve model, then we just want the fault-free behavior of the turbine. We want to get rid of all anomalous observations. Then we set the parameter to false and all the flagged data get removed. If on the other hand we want to evaluate a wind power forecast and we have observations for each turbine, and we want to evaluate these forecasts including periods of dispatch down, curtailment, or outage of the turbines, then we set the parameter to true. So we keep the anomalous data because they are anomalous, but they do reflect the actual operation of the turbine. Coming then to the cleaning algorithm of the function for the bivariate extreme values. First step is removal of instances of high power for wind speeds that are between 0 and the cutting wind speed. So for example, in this case, we would have these two dots that are between 0 and the cutting wind speed that are too high for the region they're in, and therefore they get removed. Next, the periods where there is positive power when the wind speed is above the cutout wind speed are removed. In this example, there is no such data, but they will appear to the far right of the power curve distribution. Third step, the instances of zero power output for wind speeds that are between the cut-in wind speed and the cut-out wind speed, plus or minus a certain delta, uh, get flagged. So they're flagged as anomalous, and these will be highlighted here in orange. You can see so between the cut-in plus a certain delta cut-in wind speed and the cutout wind speed, instances of zero power output are flagged as anomalous. and then other instances of low power for wind speeds between the rated and the cutout wind speed are flagged as well as anomalous. So in this case, where here between the rated wind speed and the cutout wind speed, and all the power out values that are below the rated output get flagged as well. Next, the instances of high power for wind speeds between the cutting wind speed and the rated wind speed are removed. To do so, the procedure is the following. So data are binned by wind speed. For example, here I will show bins of 1 meter per second width, but in the function they are set to a lower value to allow a more accurate detection of outliers. And on these bins, the 25th and 75th percentiles are calculated, and then the interquartile range is calculated. Sorry. For example, again, we have our distribution. We take a slice of these data. In this example, with a bin width of 1 meter per second. On these slice of data, we calculate the 25th and 75th percentiles and the interquartile range, and then we define the upper threshold as the P75 plus a certain coefficient that multiplies the interquartile range, and any value above any dot, if you like, above this threshold gets removed. Back to our example then, these are the points that within the region between the cutting wind speed and the rated wind speed, uh, these are the periods that are detected as erroneous because they fall outside the upper threshold, and so they get removed. Finally, the instances of low power when the wind speed is between the cutting wind speed and the rated wind speed are flagged. So similar procedure as in the previous step, data are binned. This time a lower threshold is defined, and observations below this threshold are flagged as anomalous. So they are not removed, they're just flagged. Back to our example then, these are the periods that are flagged as anomalous between the cutting and rated wind speed. So these are flagged but are not removed yet from the dataset. And here you can see a summary of the steps of the cleaning algorithm. Finally, as all the erroneous data have been removed, the anomalous parameter in the Python function comes into play, and if it's set equal to false, the flagged data, so the anomalous data, are removed too, whereas if it's set to true, the anomalous data are kept in the dataset. Coming then to an application of this function to a practical case, I'll present the results for the cleaning of the data from an existing wind farm that has 15 turbines. We have turbine level measurements of wind speed and active power. As I was saying, wind speed is in meters per second, power is normalized by the rated capacity. There are 2 years of SCADA data at 10-minute resolution, and the runtime for the code is around 1.3, less than 1.5 seconds anyway, per wind turbine per year of data, just to give you a reference. So in the first case, we call the function. As you see, the data set is defined as data row. We have 15 wind turbines. The parameters here are defined: cutting wind speed, rated, and cutout wind speed. We set the multiplier for the upper threshold to 2.5 instead of the default 1.5 to avoid removing too many observations. And most importantly, the anomalous parameter is set as false, which is the default anyway. So we are just keeping the unflagged data, the normal data, the erroneous data removed and the anomalous data are removed. This is what the raw data look like. And this is what the results look like. This is the wind farm power curve. So these will be the average wind speed across the 15 wind turbines and the average power across the 15 wind turbines. On the other hand, we call the function with the same parameters, but with the anomalous parameter set as true. So in this case, we do want to keep the anomalous or flagged data together with the unflagged data. And this is the result. And you can see that there is a number of instances, for example, zero power output, or these points here around the cutting wind speed, or these instances of curtailment that are kept in the data set. You can see the difference also in terms of the distributions of the values, and for the unflagged only data, so when the anomalous parameter is set to false, we have less observations in general, and especially at the higher end of the power values. And these box plots to show the different distribution of the final data, final power data, uh, depending on whether we want to keep or not the anomalous periods in the data set. Coming to the conclusions then, these function and these proposed algorithm, if you like, has some strengths and some weaknesses. The main strengths are that there's only a few parameters that need to be defined to call the function. It's relatively fast in computational terms, and it is quite simple, quite easy to include or exclude the anomalous periods from the data set, depending on what is the aim of the cleaning task. The limitations of the function are, first of all, that the raw data needs to be pre-processed to match the required formatting for the function, and that the characteristic wind speeds, so cut in, rate, and cut out wind speed, need to be set manually, either based on the manufacturer's power curve or on the judgment of the researcher. In the future, we would like to reduce the manual inputs in the function, so automatically be able to define some of the meta parameters needed for the function. So, for example, the cut in, cut out, and rated wind speed, but also the multipliers for the outlier detection. Then develop a similar algorithm for wind farm level data instead of wind turbine data. Possibly include wind direction measurements in the procedure to allow for more accurate detection of anomalous and erroneous data, and then refine the classification of anomalous data. So, for example, distinguish between curtailment periods or outage periods in the detection of in the flagging of anomalous data. And with that being said, I thank you for your attention. And as I said at the start, the code and an example for this work is in the GitHub repository that you see. And any comments, feedbacks, and contributions are very welcome. Thank you very much.